Hello, and welcome to Some Neuromind. I'm glad you found your way here tonight. Perhaps the day was long, or perhaps you're the kind of person who finds it easier to let go of the world when there's something vast and real to think about. Something so much larger than any worry that the worries quietly dissolve on their own. Either way, you're in the right place. There is nothing you need to do right now except breathe, settle, and let your thoughts drift somewhere quieter. Tonight, we're going inside our own galaxy, not observing it from a distance, not studying it in a textbook, but moving through it, slowly, gently, from its outermost edges to its hidden and restless center. We'll pass through ancient stars that remember a time before the galaxy had a shape, cross the nurseries where new suns are still being born, feel the invisible pull of forces we have never seen but cannot deny, and rest for a moment near the sleeping giant at the very heart of everything. Before we begin, if Some Neuromind helps you find rest, or gives your mind a quiet place to land at the end of the day, please consider subscribing. You're already the kind of person this channel was made for. There is a great deal to discover tonight, and before we're done, you'll encounter something that has been drifting through this galaxy for longer than the Earth has existed, and something that moves so fast it will never return. But there's no hurry. Let's go slowly. Now let's begin. The Milky Way is not the galaxy's name. It is a description. The word galaxy itself comes from the ancient Greek word for milk, galaxias, which described the pale band of light that crossed the night sky long before anyone understood what it was. Every civilization that looked up named it differently. The Norse called it the Winter Street. The Finnish called it the Path of Birds. Early Arab astronomers described it as a river of spilled light. What they were all describing, without knowing it, was the combined glow of hundreds of billions of stars seen from the inside. A structure so large that for most of human history, we had no idea we were living inside it. We named it before we understood it. That might be the most human thing about it. Our galaxy is a barred spiral, and we live in one of its quieter corners. The Milky Way belongs to a category of galaxy with a specific shape, a flat, rotating disk of stars arranged in curved arms, with a bright central region not shaped like a simple bulge but elongated into a bar, a dense band of stars stretching across the core. From above, it would resemble a pinwheel with a thick rectangular center. From the side, it would look like two fried eggs pressed back to back. We live roughly 26,000 light-years from the center, in a minor spur between two of the larger arms, a relatively calm neighborhood in a vast and sometimes violent structure. The galaxy is far older than the solar system. Current estimates place the age of the Milky Way at somewhere between 13 and 13.6 billion years, nearly as old as the universe itself. Our own solar system, by contrast, formed only about 4.6 billion years ago, meaning the galaxy had already been turning, building stars, consuming smaller neighbors, and evolving for more than 8 billion years before the sun ever ignited. The stars that existed in those early epochs were made of almost nothing but hydrogen and helium. There was no iron, no carbon, no oxygen yet. The heavy elements that would eventually become planets and life had not yet been forged. The galaxy is ancient in ways that make even geology feel recent. Some of the stars in the halo were not born here. Scattered through the vast spherical halo that surrounds the Milky Way's disk are stars that don't quite fit. They move in tilted, elongated orbits. Their chemistry is different. Almost no heavy elements, a signature of extreme age and foreign origin. Astronomers believe these stars arrived as passengers inside smaller galaxies that wandered too close to the Milky Way long ago. Captured by gravity, those smaller galaxies were slowly torn apart, and their stars were folded into the halo. These ancient wanderers now orbit our galaxy without any knowledge of where they began. They are the oldest residents of the Milky Way, and technically, they came from somewhere else. The solar system travels around the galaxy at an extraordinary speed. As you read this, the Earth is moving around the Sun is moving around the center of the Milky Way, and the entire galaxy is moving through the local universe. The Sun's speed around the galactic center is roughly 230 kilometers per second, fast enough to circle the Earth more than 5 times in a single second. Despite this speed, the galaxy is so enormous that one complete orbit takes between 225 and 250 million years. Geologists call this span a cosmic year. The last time the solar system was in roughly its current position, the supercontinent Pangaea had not yet begun to break apart, and the first dinosaurs were still tens of millions of years away from appearing. Dark matter is what holds the galaxy together. If you measured only the visible mass of the Milky Way, every star, every gas cloud, every grain of dust, and used that to calculate how fast the outer stars should be orbiting, the math would be wrong. The outer edges orbit far too quickly. They should have been flung apart long ago. The explanation astronomers have settled on is dark matter, an unknown form of mass that neither emits nor reflects light, but exerts gravity. There appears to be far more of it than there is ordinary matter. It surrounds the galaxy in an enormous, invisible halo extending well beyond the farthest visible stars. We have never seen dark matter directly. We have never detected a dark matter particle in a laboratory. We know it exists only because, without it, the galaxy would not. The center of the Milky Way holds a black hole more than 4 million times the mass of the Sun. Deep inside the galaxy, hidden behind thick curtains of dust and gas, sits a supermassive black hole called Sagittarius A star. Its mass exceeds 4 million suns, compressed into a region smaller than the orbit of Mercury. It cannot be seen directly, but its presence is unmistakable. Nearby stars trace tight, rapid orbits around an invisible point, looping through the void at speeds only possible in the presence of extreme gravity. One of those stars, designated S2, completes its orbit in just 16 years, reaching speeds of nearly 8,000 kilometers per second at its closest approach. The black hole is currently quiet, drawing in very little material. But it was not always so calm. The galactic center may have once blazed like a quasar. Evidence gathered from the structure of the Milky Way suggests that Sagittarius A* has not always been dormant. Above and below the galactic plane, vast structures of high-energy light, called the Fermi bubbles, extend for tens of thousands of light years, like 2 enormous balloons inflating from the core. These structures are thought to be the aftermath of a period of intense activity, when the central black hole was actively consuming material and releasing enormous amounts of energy. If that era occurred while life was developing on Earth, the radiation might have been detectable from our planet. It would have looked, from the right angle, like a blazing beacon at the heart of the galaxy. That fire has since gone quiet, but its echoes still glow in the sky above and below the galactic plane. The Milky Way's central region is shaped like a peanut. When infrared telescopes examine the center of the galaxy, astronomers expected to find a smooth, rounded concentration of stars. What they found instead was a shape that billows and pinches, elongated, with swells at either end and a narrowing in the middle. Viewed from the side, it resembles a peanut or a figure eight tipped on its axis. This structure is thought to have formed from a central bar of stars that gradually buckled and thickened over billions of years as stars piled up along particular orbits. The geometry is not a flaw in the galaxy's design. It is the natural result of billions of years of stars finding their equilibrium in the presence of the bar's rotating gravity. The spiral arms are not solid structures. They are patterns. One of the most counterintuitive things about the Milky Way spiral arms is that they are not made of the same stars from moment to moment. They are more like a wave than a wall. Stars drift into the arms, slow down briefly in a region of higher density, trigger new star formation in compressed gas clouds, and then drift out the other side. The arm appears to persist because new stars are always being born within it, briefly lighting it up in blue and white before aging and moving on. The structure travels through the disk at a different speed than the stars themselves. From a great distance, the galaxy appears to have stable, sweeping arms. From within, every star is simply passing through a slowly moving pattern. The sun bobs gently above and below the galactic plane as it orbits. The solar system's path around the galaxy is not a flat, perfect circle. It oscillates, drifting upward above the disk, then curving back down through it and below, like a cork floating on a very slow wave. This vertical motion is caused by the gravitational pull of the mass concentrated in the galactic plane. As the sun moves away from it, the pull draws it back, causing an oscillation with a period of roughly 64 million years. Some researchers have speculated whether these crossings of the denser galactic plane might influence the rate of comet impacts or cosmic ray exposure on Earth, though the connection remains uncertain. What is clear is that our orbit is a three-dimensional path, not a flat ring. Stellar nurseries are where the spiral arms glow brightest. The most luminous regions of the Milky Way spiral arms are not lit by the oldest stars, but by the youngest. When massive clouds of cold gas drift into the denser regions of a spiral arm, they are compressed. This compression triggers collapse, igniting nuclear fusion in cores of gas that were, until recently, simply dark and cold. The new stars that emerge are often enormous, burning at intense temperatures that make them shine blue-white. Their radiation in turn illuminates the surrounding gas, creating glowing nebulae visible from vast distances. These stellar nurseries are the galaxy's most actively creative places. Noisy, luminous, brief, and constantly producing new suns from the same raw material that has been cycling through the interstellar medium for billions of years. The Orion Nebula is one of the nearest stellar nurseries to Earth. About 1,400 light-years away, in the direction of the constellation Orion, a region of space is currently in the process of making new stars. The Orion Nebula, visible to the naked eye as the middle star of Orion's sword, contains hundreds of young stars, some still wrapped in their circumstellar disks from which planets may be forming. Some of these stars are only 1 million years old, newborns by cosmic standards. In their vicinity, gas glows pink and gold under the heat of the young sun's ultraviolet radiation. It is the nearest example of star formation we can observe in detail, and it is actively happening tonight, the same way it has been for the past several million years. Massive stars live briefly and die violently. Stars are not all alike. The smallest red dwarf stars burn their fuel so slowly that they will outlive the current age of the universe by trillions of years. The most massive stars, by contrast, are profligate. They burn through their hydrogen fuel in just a few million years, living brilliantly and dying catastrophically. When a star many times more massive than the Sun exhausts its core fuel, the collapse that follows is so rapid and so violent that the outer layers rebound in an explosion that briefly outshines the entire galaxy. This is a supernova. In the aftermath, the collapsed core becomes either a neutron star or a black hole, and the expelled material enriches the surrounding space with heavy elements forged in the dying star's interior. The galaxy's supply of iron, calcium, and gold exists in large part because of these deaths. Supernova enrich the galaxy with the building blocks of planets and life. Every atom heavier than iron on Earth was forged in the heart of a dying star or in the violent collision of two neutron stars. The calcium in your teeth, the iron in your blood, the oxygen in the air you're breathing right now. All of it was synthesized in stellar interiors and scattered by explosions across the interstellar medium over billions of years. When new stars form from gas clouds, they inherit this enrichment. Their planets, if they form, are richer in heavy elements than the first-generation worlds could ever have been. Life, at least the kind we know, requires this chemistry. It required billions of years of stellar death and recycling to make the raw materials available. We are, in a very literal sense, the product of cosmic patience. The interstellar medium is not empty. It is a complex and active environment. Between the stars, space is filled with a thin mixture of gas, dust, and plasma known as the interstellar medium. It is extraordinarily diffuse by any earthly standard. In many regions, there are fewer atoms per cubic centimeter than in the best vacuum achievable in a laboratory. But across the enormous distances of the galaxy, this material adds up to a significant fraction of the Milky Way's total mass. It is not inert. Supernovas send shock waves through it, heating and compressing it. Stellar winds sculpt it into shapes that span light years. Magnetic fields thread through it, channeling the motion of charged particles. In some regions, it cools and condenses into dark molecular clouds. In others, it glows with the heat of nearby stars. The space between stars is as dynamic as anything within them. The galaxy recycles matter continuously. Nothing in the Milky Way is wasted. When a star dies, whether gently, shedding its outer layers as a planetary nebula, or catastrophically, in a supernova explosion, the material it releases does not disappear. It mingles with the interstellar medium, cooling gradually, eventually becoming part of a molecular cloud. That cloud may eventually collapse into new stars, which form with planets, which might harbor oceans, which might, given enough time, produce organisms made of the same atoms that were once inside a sun. This cycle has been running for more than 13 billion years. Every generation of stars enriches the next. Every death is a contribution to something not yet born. The galaxy is not a static structure. It is a long, slow engine of transformation. Cold molecular clouds are the birthplaces of stars, hidden in darkness. Not all of the interstellar medium is warm and glowing. In some regions, gas and dust have settled into dense, cold clouds where temperatures drop to within a few degrees of absolute zero. These molecular clouds, so named because the cold allows hydrogen atoms to pair into molecules, are largely invisible in ordinary light. They block the stars behind them, appearing as dark patches against the brighter background of the galaxy. But they are not empty. Within them, complex organic molecules form, magnetic fields guide the alignment of dust grains, and gravity slowly gathers material into clumps that may one day collapse into stars. These dark clouds are the womb of the galaxy, silent, cold, and full of latent possibility. Some stars orbit the galaxy in the wrong direction. The vast majority of stars in the Milky Way's disk orbit the galactic center in the same direction, following the general rotation of the galaxy. But a fraction of stars, particularly those in the outer halo, orbit in the opposite direction. These retrograde stars are almost certainly not native to the Milky Way in the usual sense. They were most likely born in smaller galaxies that were absorbed into ours, arriving at odd angles that resulted in reversed orbits. They continue on their contrary paths indefinitely, moving against the flow of hundreds of billions of stars like quiet dissenters from the galaxy's general motion, carrying their foreign origins silently in the direction of their travel. Globular clusters are among the most ancient objects in the galaxy. Distributed through the halo of the Milky Way are roughly 150 known globular clusters, dense, roughly spherical collections of stars, each containing anywhere from tens of thousands to several million suns packed into a region just a few hundred light-years across. Many of these clusters are older than 12 billion years, meaning they formed in the very early universe, before the Milky Way had assembled into its current shape. Their stars are metal-poor, reflecting the chemistry of a time when the universe had not yet had enough generations of stars to produce significant quantities of heavy elements. In the center of a rich globular cluster, stars are so densely packed that the night sky, seen from a planet there, would be ablaze with thousands of stars brighter than any seen from Earth. The Milky Way is surrounded by dozens of smaller satellite galaxies. Our galaxy is not alone. Orbiting at various distances around the Milky Way are dozens of smaller galaxies, dwarf galaxies, irregular systems, and faint collections of stars that are gravitationally bound to the larger spiral. The most prominent of these are the large and small Magellanic Clouds, visible from the southern hemisphere as bright patches of the night sky. Others are far fainter, detectable only through careful surveys. Some of these satellite galaxies are currently being disrupted by the Milky Way's tidal forces, their stars being drawn out into long streams that wrap around the outer halo. The Milky Way is not a solitary object. It is the gravitational anchor of an extended family. The Magellanic Clouds may be making their first close. For decades, astronomers assumed that the large and small Magellanic Clouds had been orbiting the Milky Way for billions of years, looping around it in a long-established gravitational partnership. More recent measurements of their velocities suggest a different story. They may be moving too fast to be in a bound orbit and may instead be passing through for the first time, pulled in from the outer reaches of the local universe. If that is the case, they are not old companions, but recent visitors, and their presence is already having an effect, contributing to the warp in the outer disk and providing fresh gas that the Milky Way is slowly drawing in. The Magellanic Stream, a ribbon of hydrogen gas trailing behind them, stretches for hundreds of thousands of light years across the southern sky. The galaxy has a warp in its outer disk. The Milky Way's disk does not extend in a perfect flat plane. Beyond a certain radius from the center, it bends, curling upward on one side and downward on the other, like the brim of a hat pushed gently from below. This warp was first discovered through radio observations of hydrogen gas, which traces the disk's shape even where stars are too faint to see. Its cause is not entirely settled. The gravitational tug of the Magellanic Clouds is one candidate. The influence of dark matter clumps another. The warp rotates slowly, like a very gentle wobble in a spinning disk. From a great enough distance, the Milky Way would look slightly warped and lopsided. Beautiful, but not perfectly symmetrical. The Milky Way's disk has two distinct layers. What appears from a distance as a single flat disk is, on closer examination, a layered structure. The thin disk is the densest region, a flat plane a few thousand light years thick, filled with younger stars, open clusters, and the molecular clouds from which new stars are still forming. Above and below it lies the thick disk, older, more diffuse, populated by stars that formed earlier in the galaxy's history and that move in orbits slightly more tilted and elongated than those of their thin disk neighbors. The existence of two disk components, each with its own population of stars and its own chemical history, tells astronomers that the Milky Way's past included at least one major period of disruption, perhaps a large merger that heated and puffed up what was then the thin disk into what is now the thick one. Stellar streams trace the galaxy's history of mergers. Across the sky, when mapped with precision, are faint ribbons of stars, thin, curved arcs stretching over vast angles. These are stellar streams, the remnants of smaller galaxies or globular clusters that passed too close to the Milky Way and were torn apart by its tidal forces. As a satellite galaxy is pulled into a longer and longer arc by differential gravitational forces, its stars are smeared across the sky in the direction of the orbit, forming a ghostly trail that can persist for billions of years. Identifying and mapping these streams is one of the primary ways astronomers reconstruct the Milky Way's history of mergers and accretion. Each stream is a memory, the shape of something that once existed and was quietly taken apart. The Gaia spacecraft has transformed our understanding of the galaxy. Launched by the European Space Agency in 2013, the Gaia spacecraft has spent years measuring the positions, distances, and motions of over 2 billion stars with extraordinary precision. The data released from this mission has done more to advance our understanding of the Milky Way's structure and history than any other single project in the history of astronomy. Gaia revealed previously unknown stellar streams, confirmed the warp of the outer disk, traced the Sun's galactic orbit in remarkable detail, and uncovered evidence of ancient mergers through the motion and chemistry of halo stars. It has made the Milky Way, for the first time, into something we can map in 3 dimensions rather than simply observe from within. A major galactic merger billions of years ago shaped the Milky Way's inner structure. Using Gaia data, astronomers identified a massive disruption in the inner halo, a population of stars moving on elongated, radial orbits consistent with a large merger event early in the galaxy's history. This event, named Gaia Enceladus or the Gaia Sausage, appears to have involved the collision of the early Milky Way with a galaxy roughly a quarter of its mass, more than 8 billion years ago. The merger contributed a significant number of stars to the inner halo and may have helped trigger the formation of the thick disk by heating and puffing up the galaxy's existing stellar population. It was one of the defining events in the Milky Way's history, and its consequences are still visible in the motion of stars orbiting today. The galaxy is moving through the universe at extraordinary speed. The Milky Way is not stationary in a larger context. Along with the Andromeda Galaxy and the other members of the local group, it is falling toward a massive concentration of galaxies and dark matter called the Great Attractor, located several hundred million light-years away in the direction of the constellations Centaurus and Norma. The velocity of this collective motion, which combines the Milky Way's own orbital motion, the local group's motion, and the pull of the Great Attractor, amounts to roughly 600 kilometers per second relative to the cosmic microwave background. In a universe where everything is moving, the Milky Way is no exception. It falls, drifts, and accelerates, embedded in a structure of gravity that extends far beyond the horizon of any single galaxy. The Milky Way and Andromeda will collide in about 4.5 billion years. The Andromeda Galaxy, visible to the naked eye as a faint smear of light in a dark sky, is currently moving toward the Milky Way at roughly 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will begin to interpenetrate in a collision that will unfold over several billion more years. Because the distances between individual stars are so vast, almost no stars will actually collide directly, but the shapes of both galaxies will be dramatically distorted. Tidal tails will stream outward for hundreds of thousands of light years. The central black holes will eventually find each other and spiral together. After many billions of years, what remains will be a merged elliptical galaxy, the two spirals having dissolved into a single, rounder, calmer system. Hypervelocity stars are flung from the galaxy's center at escape velocity. On rare occasions, a binary star system wanders too close to Sagittarius A*, the supermassive black hole at the Milky Way center. In the intense tidal field of the black hole, the binary pair is disrupted. One star is captured into a tight orbit, while the other is slingshot outward at such enormous speed, sometimes exceeding 700 kilometers per second, that it can escape the Milky Way's gravity entirely. These hypervelocity stars travel alone through the outer halo and eventually into intergalactic space, never to return. They carry no companion, no planetary system, nothing but velocity and the memory of the violent encounter that launched them. They are the only stars in the galaxy that have been given one-way tickets to the void. The Fermi bubbles extend above and below the galactic center for 25,000 light-years. Discovered in 2010 through observations by NASA's Fermi Gamma-Ray Space Telescope, the Fermi bubbles are two enormous lobes of high-energy radiation extending symmetrically above and below the galactic plane, centered on Sagittarius A star. Each lobe spans roughly 25,000 light-years, about a quarter of the galaxy's diameter. Their origin is still debated. They may have been inflated by a period of intense activity from the central black hole millions of years ago, or they could be the result of a sustained burst of star formation in the galactic center that drove powerful outflows into the halo. Invisible to ordinary telescopes, they dwarf most of what we consider familiar in the galaxy. The Milky Way has a hidden anatomy far larger than its visible disk. Pulsars are among the most precise natural timekeepers in the universe. When a massive star collapses into a neutron star, the resulting object may be spinning at extraordinary rates, some complete hundreds of rotations per second. If the neutron star's magnetic axis is offset from its rotation axis, it sweeps a beam of radio radiation across space like a lighthouse, detectable from Earth as a regular, periodic pulse. These are pulsars, and their timing can be so regular that some rival atomic clocks in precision. Astronomers use arrays of pulsars across the Milky Way as a kind of cosmic timing network, monitoring tiny variations in pulse arrival times that could reveal the passage of gravitational waves rippling through the galaxy. Pulsars are remnants of death, but they have become instruments of extraordinary scientific precision. The interstellar medium contains complex organic molecules. In the cold molecular clouds of the Milky Way, chemistry happens in darkness. Radio observations have detected hundreds of distinct molecular species in these clouds: water, ammonia, formaldehyde, ethanol, and increasingly complex organic compounds. These molecules form on the surfaces of dust grains under the influence of ultraviolet radiation, then are released back into the gas phase as conditions change. Some of these compounds, polycyclic aromatic hydrocarbons, amino acid precursors, simple sugars, are the chemical ancestors of biology. When a star forms from one of these clouds, it inherits this chemical legacy. The gas and dust from which Earth formed came from such a cloud, and some of those organic molecules may have been present from the beginning, long before the first cell divided. The galaxy's magnetic field is woven through the entire disk. Threading through the Milky Way, largely invisible but measurable through its effects on radio waves and the alignment of dust grains, is a large-scale magnetic field. It follows the structure of the spiral arms, twisting and branching as it goes, reaching up into the halo and influencing the flow of charged particles through the disk. This field is generated by the combined motion of charged matter across the galaxy, a kind of enormous, slow dynamo driven by the rotation of gas and plasma. Its strength is billions of times weaker than a refrigerator magnet, but over galactic distances and cosmic timescales, it shapes the trajectories of cosmic rays, influences the formation of molecular clouds, and leaves measurable patterns in the light from distant stars. Cosmic rays from across the galaxy pass through your body right now. At this moment, streams of high-energy particles, mostly protons and atomic nuclei, but also electrons, are raining down through the atmosphere and passing through everything at ground level, including you. These are cosmic rays, accelerated to near-light speeds by exploding stars, pulsar winds, and other energetic processes distributed across the Milky Way and beyond. Most pass through matter without any interaction at all. Occasionally, one collides with an atomic nucleus in the upper atmosphere, triggering a cascade of secondary particles that reach the ground. Detectors buried deep underground, like the Ice Cube Observatory at the South Pole, capture a few of these particles per day, not from the atmosphere, but from space itself, passing directly through the Earth. The galaxy is continuously sending messengers through us. Some stars were formed before the Milky Way had a disk. The flat spiral disk we think of as defining the Milky Way did not exist from the beginning. In the galaxy's earliest epochs, before it had settled into a rotating structure, star formation occurred in a more chaotic, distributed way, in clumps and clouds spread through a loose, roughly spherical system that was still assembling itself under gravity. Stars that formed in that early era now reside mostly in the thick disk and halo, having been there since before the thin disk existed. They are the elders of the galaxy, formed under conditions that no longer exist, moving through a structure that built itself up around them over billions of years. Their compositions and orbits carry the imprint of a Milky Way that was younger, more chaotic, and still becoming itself. Open star clusters are nurseries that eventually dissolve. When a giant molecular cloud collapses and ignites into a cluster of new stars, those stars begin their lives together, sharing a common origin and a common motion through space. These open clusters, named for their loosely scattered appearance, persist for millions or even hundreds of millions of years before the tidal forces of the Milky Way, combined with close encounters between stars, gradually pull them apart. Stars peel away from the cluster one by one over time, spreading out into the surrounding field. Today, they are invisible among the vast population of stars in the disk, indistinguishable without careful analysis of their chemistry and motion. Our own sun likely left its birth cluster long ago, its siblings now lost somewhere in the galaxy. Variable stars serve as rulers for measuring galactic distances. Certain types of stars pulsate, expanding and contracting in a regular cycle that changes their brightness in a predictable way. Among the most useful are Cepheid variable stars, which follow a precise relationship between how quickly they pulse and how intrinsically bright they are. By measuring the period of a Cepheid's pulsation, astronomers can calculate its true luminosity, and by comparing that to how bright it appears from Earth, they can determine its distance. This method, developed by Henrietta Swan Leavitt in the early 20th century, was fundamental to establishing the scale of the galaxy and, later, the scale of the universe. Variable stars are not just interesting objects. They are the measuring sticks with which astronomy learned to gauge the size of everything. Neutron stars can spin hundreds of times per second. When the core of a massive star collapses in a supernova, the resulting neutron star inherits all of the angular momentum of the original stellar core, compressed into a sphere roughly 20 kilometers across. Conservation of angular momentum causes it to spin extremely rapidly, in extreme cases, completing hundreds of full rotations every second. These millisecond pulsars are the fastest spinning solid objects known to science. Some are thought to have been spun up to these extreme rates by accreting matter from a binary companion over long periods of time, gaining angular momentum from the infalling material like a wheel given a sustained push. At their equators, the surfaces of these stars are moving at a significant fraction of the speed of light. The galactic bar rotates slowly and drives gas toward the center. The central bar of the Milky Way, the elongated structure of stars crossing the core, is not a fixed feature. It rotates, though more slowly than the stars in the inner disk. As it turns, it exerts a gravitational influence on the gas within its reach, creating resonances that funnel material along specific paths. Some of this gas flows inward toward the galactic center, potentially providing fuel for bursts of star formation in the central molecular zone or for the occasional feeding of Sagittarius A star. The bar is, in this sense, an engine within an engine, a rotating structure that redistributes the galaxy's raw material and periodically stirs the conditions needed for dramatic activity at the core. The co-rotation radius may be one reason complex life exists near our Sun. In the Milky Way, the spiral arms rotate at a fixed pattern speed, while individual stars orbit at speeds that vary with distance from the center. At one particular distance, the co-rotation radius, the orbital speed of stars matches the pattern speed of the arms. Stars at this distance spend relatively little time inside the denser, more dangerous spiral arms, where supernova rates are higher and gravitational disturbances more frequent. The Sun's orbit places it close to this co-rotation radius. This may mean that the solar system passes through spiral arms less frequently than it would at other galactic radii, spending more time in calmer, quieter regions of the disk. Whether this matters for life is uncertain, but it is a striking coincidence, or perhaps not a coincidence at all. The galaxy breathes through a cycle called the galactic fountain. The disk of the Milky Way is not a closed system. Supernova explosions and the combined stellar winds of massive young stars deposit enormous amounts of energy into the surrounding interstellar medium, heating gas and driving it upward out of the plane of the disk. This hot gas rises into the lower halo, where it cools gradually, condenses, and eventually falls back down into the disk as cooler clouds. This circulation, known as the galactic fountain, redistributes heavy elements from stellar death throughout the disk, regulates the temperature and pressure of the interstellar medium, and continuously mixes the material available for future star formation. The disk does not just spin. It exhales heated gas upward and inhales cooled material back down, breathing in a cycle that unfolds over millions of years. Not all of the Milky Way's mass is in its disk. If you were to weigh the Milky Way by counting only its visible stars and gas, you would arrive at a serious underestimate. The dark matter halo that surrounds the galaxy extends far beyond the farthest visible stars, swelling to a volume many times larger than the luminous disk. Within this vast halo, the actual count of ordinary matter is sparse. A few ancient stars, some globular clusters, occasional wisps of hot gas. But the dark matter permeates it entirely, and the gravitational mass of the halo dwarfs that of everything we can see. When astronomers attempt to measure the total mass of the Milky Way, using the orbits of distant satellites and the velocities of halo stars. Estimates range widely, but all of them require a halo of dark matter that outweighs the visible galaxy by a large factor. There may be billions of rogue planets drifting through the galaxy. Planets are not always permanent members of a solar family. In the early life of a planetary system, gravitational interactions between forming planets can fling one of them onto an escape trajectory, ejecting it from the system entirely. Once free, it travels through the galaxy without any star to warm it, slowly cooling over billions of years. Current statistical estimates suggest that rogue planets may be extremely common, possibly more numerous in the galaxy than stars themselves. Most would be utterly dark and cold, detectable only by gravitational microlensing, the brief bending of background starlight as they pass in front of it. But some, particularly those with thick hydrogen atmospheres that trap internal heat, might maintain subsurface temperatures above freezing. Worlds in the dark, traveling in silence. Dust in the galaxy blocks our view in visible light, but can be seen in infrared. The dust grains of the interstellar medium, tiny particles of carbon, silicates, and ice, are extraordinarily effective at absorbing and scattering visible light. A region of space with even a modest column of dust can block the light of stars entirely, creating dark patches in the sky that observers sometimes mistake for gaps in the star field. These dark nebulae are not absences of stars, but curtains of dust preventing the stars behind them from being seen. Infrared light, with its longer wavelengths, passes through dust far more easily, allowing infrared telescopes to peer into regions that are opaque in visible light. The center of the Milky Way is entirely obscured in visible wavelengths. It can only be studied in infrared, radio, and X-ray. Binary star systems are more common than single stars. Our Sun orbits alone, without a stellar companion, which might feel like the standard arrangement. But across the galaxy, most stars are not solitary. The majority belong to binary or multiple systems, two or more stars orbiting their common center of mass, sometimes in nearly circular orbits close together, sometimes in wide, eccentric paths that take them very far apart. Binary systems have significant consequences for stellar evolution. Stars can transfer mass to one another, triggering nova explosions. White dwarfs can accrete enough material from a companion to explode as type I supernovae. Massive pairs can spiral together and eventually merge, producing gravitational waves detectable across the universe. Solitude, among stars, is somewhat unusual. The Milky Way structure is lopsided in several ways. Perfect symmetry is rare in nature, and the Milky Way is no exception. One side of the outer disk is thicker than the other. The spiral arms are uneven in length, brightness, and structure. The central bar is not precisely aligned with the galaxy's symmetry axis. The stellar halo is slightly off-center relative to the disk. These asymmetries are not defects. They are the accumulated result of billions of years of mergers, tidal interactions with satellite galaxies, and the uneven distribution of dark matter around the galaxy's outer reaches. The Milky Way has the characteristic imperfections of something old and complex, a structure that has grown not from a single, simple plan, but from countless events, disruptions, and gradual recoveries. Radio telescopes reveal structures invisible in ordinary light. Before the era of radio astronomy, the Milky Way was mapped almost entirely through what could be seen. The distribution of stars, the glow of nebulae, the darkness of dust clouds. Radio waves changed everything. Cold hydrogen gas, distributed throughout the disk in quantities invisible to optical telescopes, emits a characteristic radio signal at a wavelength of 21 centimeters. By mapping this signal across the sky and measuring the Doppler shifts in its frequency, astronomers were able to construct a three-dimensional picture of the galaxy's gas distribution, and through it, the structure of the spiral arms for the first time. Radio observations also revealed the Fermi bubbles, the properties of the galactic center, the extent of the Magellanic Stream, and countless other features that ordinary light would never have shown. The galaxy's oldest known stars approach the age of the universe itself. Among the faint stars scattered through the Milky Way's halo, astronomers have found individuals whose ages approach or may exceed 13 billion years. These stars were identified through their chemical composition. Their spectra reveal almost no elements heavier than helium, meaning they formed before more than 1 or 2 generations of stars had had time to enrich the surrounding gas with heavier elements. They formed, in other words, very close to the beginning. Stars this old are sometimes called metal-poor or, in the most extreme cases, hyper-metal-poor stars. Each one is a living relic from the universe's earliest chapter, still fusing hydrogen in a galaxy that has changed almost beyond recognition since the night they first ignited. Planets form naturally wherever stars do. For most of history, it was an open question whether our solar system was typical or exceptional. The discovery of the first confirmed exoplanets in the 1990s, followed by thousands more from the Kepler and TESS space missions, has settled the question decisively. Planets are not rare. They are the expected outcome of star formation. Statistical analysis suggests that on average, every star in the Milky Way hosts at least one planet. With several hundred billion stars in the galaxy, that implies a comparable number of worlds. Some of these planets orbit in the habitable zones of their stars, where liquid water could exist on their surfaces. Whether any of them host life, simple or complex, is the question that astronomy has not yet answered. But the raw number of opportunities is vast. The Milky Way contains regions where star formation has already ended. Not every part of the galaxy is equally productive. In older regions, particularly in the thicker disk and inner halo, the gas supply has been largely consumed or dispersed. Star formation in these areas has slowed to a trickle or stopped entirely. The stars that remain are aging populations, redder, cooler, and older than the blue-white giants of the active spiral arms. Over billions of years, more and more of the galaxy will transition into this quieter state. The Milky Way's star-forming epoch, already past its peak by several billion years, continues to wind down gradually. The galaxy is not dying, but it is, in a slow and stately way, entering a calmer phase of its life. Some molecular clouds contain the chemical precursors of life. Deep within the cold, dense cores of the Milky Way's molecular clouds, radio telescopes have detected the signatures of increasingly complex organic molecules. Glycine, the simplest amino acid, has been tentatively identified in the interstellar medium. Phosphorus, essential for DNA and cell membranes, has been found in stellar outflows. Ribose and other simple sugars have been detected in meteorites thought to have formed from interstellar material. These detections do not mean life exists in molecular clouds. Conditions there are far too hostile for life as we know it. But they suggest that the chemistry leading toward life begins not in the ocean or on a planetary surface, but in the cold, dark spaces between stars, seeding the clouds from which new solar systems will one day condense. The galaxy's rotation does not follow the pattern expected from its visible mass. One of the most important observations in modern astronomy is also one of the simplest to state. When you measure how fast stars orbit the galaxy at different distances from the center, the outer stars move too fast. In any ordinary gravitational system, Objects farther from the center should orbit more slowly, just as Neptune orbits the Sun far more slowly than Mercury. But in the Milky Way, and in nearly every other galaxy measured, the rotation speed stays roughly constant even at very large radii, rather than dropping off as expected. This flat rotation curve is one of the primary pieces of evidence for dark matter. No alternative explanation has succeeded in accounting for it without invoking some form of unseen mass distributed throughout the galaxy's halo. The galaxy is not the same as it was for the dinosaurs. The Milky Way evolves on timescales that dwarf human history. In the 250 million years it takes the solar system to complete one orbit, a single cosmic year, galaxies form and dissolve, stars live and die by the millions, and the overall structure of a galaxy can shift significantly. When the first non-avian dinosaurs appeared on Earth, the solar system was in a different part of its galactic orbit, surrounded by a different local population of stars. The constellations we see today did not exist then. They are a temporary arrangement, unique to this moment in the sun's journey. What we call the night sky is a fleeting snapshot of a galaxy in continuous motion, and every generation of observers has a different view. The night sky you see represents only a tiny fraction of the galaxy. On the clearest night, far from city lights, the human eye can detect roughly 5,000 individual stars. The Milky Way contains at least 200 billion, with some estimates approaching 400 billion. The 5,000 stars visible without a telescope represent a fraction so small it barely registers, less than 0.03% of the total. Nearly all the rest are hidden either by distance, by dust, or by the simple limit of human visual sensitivity. The faint band of light we call the Milky Way on a dark night is not the galaxy. It is just the combined, unresolved glow of billions of stars too far away to see individually, viewed along the compressed thickness of our galactic disk. We live inside something we can barely glimpse. The Milky Way's age can be estimated from its oldest stars in the age of the universe. One of the most elegant cross-checks in astronomy involves comparing the ages of the oldest stars in the Milky Way, calculated from their luminosity, temperature, and composition, with the independently measured age of the universe derived from the cosmic microwave background. The oldest globular cluster stars appear to be roughly 13 billion years old. The universe is 13.8 billion years old. The Milky Way, or at least its first stars, must have formed within a few 100 million years of the Big Bang. This agreement, achieved through completely independent methods, is one of the quiet triumphs of modern cosmology. The galaxy is nearly as old as time itself, having formed while the universe was still in its earliest creative burst. The Sun's galactic orbit has not been smooth and unchanging. Over its 4.6 billion-year history, the solar system has not drifted serenely through an unchanging galactic neighborhood. As the galaxy has evolved, absorbing satellite galaxies, developing and reshaping its spiral arms, experiencing bursts of star formation in the inner disk, the environment through which the Sun orbits has shifted. The local density of stars, the intensity of cosmic ray bombardment, and the rate of nearby supernova have all varied over geological time. Some researchers have investigated whether these variations correlate with episodes of mass extinction or climate change on Earth, though establishing a clear causal link remains difficult. What is certain is that the galactic environment the solar system experiences today is not the same one it experienced at the dawn of life, or even at the time of the dinosaurs. The chemical composition of stars reveals which generation they belong to. Astronomers classify stars in broad generations based on their metal content, or metal, in the astronomical sense, means any element heavier than helium. The very first stars, called Population 3, contained almost nothing but hydrogen and helium, because no heavier elements existed yet. When they died in supernova, they scattered newly created metals into the surrounding gas. The second generation, Population 2, was slightly enriched. Our Sun and the younger stars around us are Population 1, relatively metal-rich, born from gas that had already passed through multiple cycles of stellar life and death. The Sun's relatively high metal content is what allowed the formation of rocky planets and, ultimately, a chemistry complex enough for life. The galaxy's disk warps and ripples in ways that are still being studied. Beyond the more familiar warp of the outer disk, recent surveys of stellar distances and motions have revealed additional structure. The disk appears to ripple, with waves moving through it like the surface of a disturbed pond. These vertical oscillations in the galactic disk were first clearly identified using data from surveys of red giant stars, which can be detected at enormous distances because of their brightness. The ripples extend for thousands of light years and appear to be moving outward from the inner galaxy. Their origin may be related to the passage of a satellite galaxy through the disk or to perturbations from dark matter substructure. They are one more reminder that what looks, from a distance, like a smooth and orderly spiral is, on closer examination, a dynamic and continuously responding structure. Gravitational waves from neutron star mergers carry signatures of the galaxy's heaviest elements. When two neutron stars collide in what astronomers call a kilonova, the event produces both gravitational waves and an intense burst of light. In that brief explosion, which may last just a few seconds, more gold may be produced than exists in the entire Earth. These heavy elements are ejected into space at high velocity, eventually mixing with the interstellar medium. Stars that form later from gas containing this material inherit traces of it. By detecting gravitational waves from neutron star mergers and matching them to optical observations, astronomers have been able to confirm that a significant fraction of the gold, platinum, and other heavy elements in the Milky Way originated in these rare and violent events. The ring on your finger, if gold, carries the memory of a collision between two dead stars. White dwarf stars are cooling records of the galaxy's past. When a sun-like star exhausts its nuclear fuel and sheds its outer layers, the remnant left behind is a white dwarf, a hot, dense object roughly the size of Earth, supported not by fusion, but by the quantum pressure of electrons resisting compression. White dwarfs cool over billions of years, growing dimmer and redder as they do. The coolest, faintest white dwarfs observed in the Milky Way's disk and halo are among the oldest objects in the galaxy, their temperatures recording how long they have been cooling since their parent stars died. By measuring the distribution of white dwarf temperatures, astronomers can estimate when star formation began in different parts of the galaxy. The cooling curves of white dwarfs are, in effect, the galaxy's thermometers of the past. The galaxy generates and disperses its own radiation environment. The Milky Way is not just a collection of stars. It is a self-modifying radiation environment. Supernova produce cosmic rays that stream through the disk, affecting the chemistry of molecular clouds and potentially influencing mutation rates in living organisms over very long timescales. The deaths of massive stars drive stellar winds that sweep out cavities in the surrounding gas. The central black hole, even in its current quiet state, heats gas in the inner regions. Magnetic fields channel and redirect charged particles. The galaxy continuously modifies the physical conditions within itself through the collective behavior of its stars, and these conditions in turn affect where and how new generations of stars and planets form. The Milky Way is not a passive container. It is an active participant in shaping what emerges within it. The number of stars in the Milky Way is estimated, not counted. When someone states that the Milky Way contains 2 to 400 billion stars, that number is an estimate based on measurements of the galaxy's total luminosity, combined with assumptions about the distribution of stellar masses. Individual stars cannot be counted directly. They are too numerous, many are too faint, and much of the galaxy is obscured by dust. The uncertainty in the estimate is itself large. The Milky Way might contain as few as 100 billion stars or as many as 400 billion, depending on how many faint, low-mass red dwarfs are assumed to exist in the disk and halo. These red dwarfs are individually very dim, but may collectively contribute a significant fraction of the total stellar population. The galaxy is not fully counted and may never be. The chemical evolution of the Milky Way is written in its stars. By observing thousands of stars at different distances from the galactic center, astronomers have pieced together a picture of how the Milky Way's chemical composition has changed over time and across space. Stars near the center tend to be more metal-rich than those in the outer disk, reflecting the higher density of star formation and supernova enrichment in the inner galaxy over billions of years. Stars in the halo tend to be metal-poor, reflecting their early origin before many enrichment cycles had occurred. The thick disk stars occupy an intermediate position, both in chemistry and in age. Mapping these gradients across the galaxy's structure reveals the history of star formation itself, where it happened, when it was most intense, and how the products of stellar death have spread outward over billions of years. The Milky Way's future includes a long, slow decline in star formation. The golden age of star formation in our galaxy, when new suns were igniting at their greatest rate, occurred billions of years ago. Since then, the pace has declined steadily as the supply of cold gas available for star formation has been gradually consumed, dispersed, or locked up in stellar remnants. New stars are still forming, including in regions like Orion visible tonight, but the rate is far lower than it once was. In the distant future, as the remaining cold gas is exhausted and no fresh supply arrives to replace it, the Milky Way will gradually transition into a galaxy that is purely aging. No new suns, only the slow cooling and fading of those already lit. That future is billions of years away, but the trajectory is already visible in the data. And so we come gently to rest, as we always do, here inside the disk of our galaxy, one quiet star among hundreds of billions, surrounded by ancient light and invisible forces and the slow, patient turning of everything. Tonight you drifted through stellar nurseries where new suns are being born. You passed the site of ancient mergers, their stars still orbiting in memorial streams. You came close to the sleeping giant at the galactic center and flew alongside stars moving so fast they have already left home forever. You moved through dark clouds holding the chemical seeds of life, and through a halo of ancient stars that remember a time before this galaxy had its current shape. The Milky Way is not a backdrop. It is the place you live, and it is alive with motion, history, and consequence in every direction from here. The atoms you are made of have been through this galaxy before, inside other stars, other clouds, other moments in this long unfolding story. Tonight they are arranged into you, briefly, quietly, aware enough to wonder about where they came from and what surrounds them. Let that thought settle now. Let your breath slow. The galaxy will keep turning. The stars will keep their patient vigil. Nothing is required of you until morning. Consider subscribing to Some Neuromine. You're already the kind of person this channel was made for. But for now, let go. Rest now. You've earned it. Good night.